Hello class, today we are going to go over Unit 7 lesson number 2 and it's going to be 7.2 compound angle formulas. So I know there are a lot of formulas that we learned in 7.1 and just as a warning there are going to be more, so every lesson kind of develops new formulas and those are all going to be helpful when we have to work with trig identities this course. But remember, you can always have your formula sheet with you, so you never have to memorize these, but they will become very familiar to you enough where you don't have to reflect back on your formula sheet. All right, so just to review, these identities we learned in 7.1, the ones related to symmetry, and then cofunction identities, which we also referred to as complementary angles, complementary angle identities. I'm bringing these up again because we're going to go over the formulas for compound angles today, and developing those formulas will require us to use these two identities. So cofunction, that was when you had one angle of theta and one angle of pi over 2 minus theta. So for that one, remember sine and cos always were equivalent there. So sine of theta was equivalent to cos of its complementary angle, pi over 2 minus theta. Same for cos theta, it swapped, so it was equal to sine of pi over 2 minus theta. And then tan theta, remember, had to do with its reciprocal function. So cotangent theta was equal to, tan theta was equal to cotangent of the complementary angle. Identities related to symmetry. So remember, because sine was odd, that means the rule holds that sine negative theta then is equal to negative sine theta. Cos is even, so cos negative theta was equal to cos positive theta. And tan had odd symmetry, so tan negative theta was equal to negative tan theta. Okay, so we're going to come back to those on the next page. All right, so what is the objective of trigonometry? It is often to find the exact value of a trig ratio. So that means we want to be able to find a value without using a calculator. So that means no decimals and radicals are okay. So using special triangles, that is when we know the exact values of angles. Right, so that's when we work with pi over 3, remember that's 60, pi over 4, 45, and pi over 6, 30. So any of these three here is when that help us work with special triangles and exact values. So our problem is, though, obviously all diagrams and angles are not always just going to be 60, 45, and 30. So for example, how can we find the exact ratio of something like sine 75? Okay, so that doesn't fall in these three categories. So one method is to write 75 degrees in terms of special angles that we can find the exact value of. So what is a way that we can write 75 degrees in terms of 60, 45, or 30? So for example, if you wanted to find sine of 75 degrees, we can write this as sine of, and then maybe we can write 75 as 45 plus 30 degrees. Okay. Obviously, this unit we're working in radians, so let's get used to that. So I could give you, instead of saying sine 75, I would give you, say, sine 5 pi over 12. Okay. And at the side, you could do your conversions to see that this represents 75 degrees. Okay. So this basically means 5 sets of pi over 12, and pi over 12 represents 15, and then 5 times 15 would give you the 75. Okay, so if I wanted to rewrite this side now in terms of radians, that would be sine of bracket pi over 4 plus pi over 6, right? Pi over 4 is the 45, pi over 6 is the 30. However, we do not know how to solve something like this. Okay, do not think, so I always still, even after we go through this this lesson, students think that they can distribute sine into both parts. Okay, so sine is not distributed. Okay, and today's lesson will show you the formula you have to use. Okay, so what I mean by that is I'm saying that it does not equal sine pi over 4 plus sine pi over 6. Okay, that's what I mean. So it's not equal to that. Big red no. Okay. So that's what today's lesson is about, is if I can write this number in terms of the addition or subtraction of some special angles, what am I supposed to do next? So what is the formula to solving something like this? So we are going to need another method to help us solve for the ratio, and this will help us be now exposed to the compound angle formula. So a compound angle, so usually when you say compounded, that means multiple items or two things put together. So a compound angle is an angle that is created by adding or subtracting two or more angles. Okay, also I want you to keep in mind, so up here we added and subtracted some special angles. So it can be 45 plus 30, we can do 45 plus 60, we can do 60 minus 45, there's plenty of options. But keep in mind it can also be multiples of special angles too. So what I mean by that is, for example, if I had us work with 165 degrees, and in radians that would be 11 pi over 12. If I had us try to rewrite this in terms of special angles, you're going to notice that we can't add them all up. So like, for example, I can't do 60 plus 45 plus 30 and get 165. But I can realize that I can write 165 as 2 times 60 degrees, so 2 sets of 60, which would give me 120, and then 120 plus 45 would give me the 165. So that's what I mean about multiples of special angles. You can do something like that. So how would I write 11 pi over 12 in radians as an addition or subtraction of two angles? I would write it as 2 times pi over 3, right? 2 sets of 60 plus pi over 4. Okay. So it may just be singular, like up here, or it may be multiples, like here it was a multiple of pi over 6. Okay, so we start off by just giving you the compound angle formula for cos A minus B. Okay, so that is if you are subtracting two special angles. So A and B are some type of angle. So for example, at the side here, that would be like if I gave you cos pi over 12. And you had to rewrite cos pi over 12 as the addition or subtraction of two angles. So you would think pi over 12 is 15 degrees, right? So how can I write that using special angles? Well, here I decided to do 45 degrees. Okay, so 45 minus, and that's 30. And I know that equals 15. So I rewrote cos pi over 12 as cos pi over 4 minus pi over 6. Okay, those are equivalent. So the formula for solving something like this is here. Okay, so you break it up. You do cos A times cos B. So cos of the first angle times cos of the second angle, plus, okay, so it's always, the sign here is always opposite of what's there, plus sine A times sine B. So so plus sine of the first angle times sine of the second angle. And we're obviously going to go over examples where we do that later, but that is our general formula. So notice that is not the same as, you know, what our natural instincts are to think up here, that we distribute sine in, and that's not the case. If you do that, you will get the wrong answer. So you have to use this formula. Okay. Where A is the first angle, B is the one being subtracted. All right, let's turn to the next page. The formula for cos A plus B is going to be very similar to that of cos A minus B. So it's going to be similar in the fact that you are going to have to still do cos A times cos B. And the difference is that instead of a plus in between, you're going to have a minus. So you're going to have minus, and then the same as the other part, sine A times sine B. Okay, so it's that minus sign. So a rule I like to use for cos is I always think the cos compound angles always have the coses multiplied and then the sines multiplied. And for cos, the formulas, whatever sign you see in the middle is always the opposite of what happens in between here. Okay. All right, so now I'm going to show you where this came from. Okay. You don't have to memorize these proofs. I am just doing this for those that are curious as to where this formula comes from. Okay, and actually going over this is really good practice for simplifying trig identities in our later lesson because it gets you familiar with breaking things down and applying different identities to new scenarios. Okay, so this is good and beneficial practice for you. So, cos A plus B. Where does this formula come from? I could actually write cos A plus B as cos A minus negative B, right? So I haven't changed the formula here. Two negatives still make a positive. But when I've written it as cos A minus negative B, follow my green arrow here, now I've made it look like the formula on the previous page, right? So now it looks like cos A minus B formula, right? Which is this. Cos A times cos B plus sine A times sine B. However, in this scenario, in my scenario here, the B is really negative B. So wherever there's a B here, I'm going to put negative B because that's what it's become. Okay? So that's exactly what I've done here. I've done cos A times cos negative B plus sine A times sine negative B. All right, so what can we do next? We don't like typically to have like negative angles inside here. So that's when you're thinking to yourself, all right, what identities deal with negative versions of angles? So that is the symmetry identities from the previous page. So I've rewritten it here. I know that based on the symmetry identities, cos negative theta is equal to cos theta because of its even symmetry. So I can replace that. And I know sine negative B, okay, can actually be written as negative sine B because sine of a negative angle is equal to negative sine of that angle. So I can rewrite it like this. Okay. So that stays. This just becomes cos positive B plus sine A stays the same. And this I'm going to rewrite as negative sine B. All right, so those two will be multiplied the same. And now a positive times a negative equals a negative. So it becomes minus sine A times sine B. And that is the red formula that I've written up here. So we just used one of the compound angle formulas and the symmetry identities to help us get a new formula for cos A plus B. All right, so we've dealt with cos. Now let's deal with sine. So sine A minus B. So the formula for that, and then I'm going to go over it after, a little different from cos. So cos formulas always keep the coses together and the sines together. Sine is going to switch that. So sine A minus B is going to be sine A times cos B. Okay, sine of the first, cos of the second. And then in sine, in cos formulas, you always switched the sign that appeared here to the one here. In the sine formulas, you've maintained the sign that you see in the brackets. So you're going to do minus. And then we're going to kind of flip. You're going to do cos of the first angle, sine of the second angle. So as you see in the sine formulas, the sine and cos are jumbled together. So mixed up, but maintain the same sign. All right, so let's go over where this came from. And again, here we're going to have to refer to the cofunction identity. All right, so let's pretend that sine A minus B, let's call theta A minus B. Okay, so theta is going to be A minus B. According to the cofunction identity, okay, so I'm going to go right here. Do this in purple a bit. Okay, so according to this cofunction identity here, sine of theta is equal to cos of pi over 2 minus theta. So that's what I've done here. I've written sine of theta, which is A minus B, as cos pi over 2 minus theta, right? This is theta, essentially, A minus B. Okay? All right, so this is just theta here. All right, so if I were to expand that a little bit, so if I were to distribute in, let's use a different color here, orange. If I were to distribute in the negative here, so it would be negative A and then negative times negative B. Okay. I would get cos of pi over 2 minus A plus B. Okay. Oops, sorry, I moved this one down. Okay, now I want us, so we've used cofunction, now I want us to look at this new formula, and I want us to analyze this as if it were cos A plus B. Okay, so I want you to pretend that your A, right, of cos A plus B is really pi over 2 minus A, and then your B is this B right here, so just the way it looks. So if we plug this into our cos A plus B formula, we are going to get, delete this here, we're going to get, so it's always cos A, so cos pi over 2 minus A times cos of the second, okay, minus, right, remember if cos has a plus, then it switches in here, minus sine of the first part, pi over 2 minus A, times sine of the second part, B. All right, so now we're actually going to use cofunction identity again. Okay, that's why I've highlighted in purple here, so you can look over here at the side. All right, you should be thinking, okay, I know that anything where it's cos pi over 2 minus A, right? So that would be kind of this variation here. That's equivalent to sine of that one angle. So this is equivalent to sine of A, according to the cofunction identity. And then cos B remains. And then we have minus, and then sine pi over 2 minus A looks like this, sine pi over 2 minus theta, which is equivalent to cos theta. So if I translate that to here, that would be equivalent to cos of A. And then the sine B stays. And what do you notice? This last final line is the equation that I gave you at the top here. Okay. So you got to see how this formula is developed based on other formulas and identities. All right, sine A plus B. For these next ones, I'm just going to give you the formulas. You can kind of see the idea. They're all very much derived in these similar ways. So sine A plus B is going to follow the same pattern as up here, where sine and cos are combined and cos and sine are combined. And then you maintain the sign that you see. So sine A plus B is sine A times cos B plus cos A times sine B. Now the tan ones, unfortunately these ones have to deal with a rational expression, so we're going to have a numerator and denominator. So tan A minus B is represented as tan A minus tan B, okay, in the numerator, so you maintain the symbol here for tan, divided by 1 plus, so notice these two switch, the signs switch, 1 plus tan A times tan B. Following that same pattern, we should be able to come up with tan A plus B. So kind of do the same thing up here. So the numerator for this one's going to be tan A plus tan B. And then the denominator, same kind of pattern as up here, is going to be 1 minus tan A times tan B. Okay, so those two symbols always swap. All right, so let's try some examples applying these on the next page. All right, so it says determine the exact values of all of these. And we're going to have to use the compound angle formulas. So just keep in mind that exact values means that most likely you're going to work with special triangles, there's going to be no decimals, and you are not to be using a calculator. Okay, so you should never have to use it if you've broken it down properly. Because we're going to have to use special triangles, I've drawn them in for us here, and everyone should do that on their page. So 1, 1, root 2 with the 2 pi over 4s in both angles, and then we have the root 3 opposite pi over 3, pi over 6 with 1 opposite it, and then 2 is the hypotenuse. Okay, so let's start off. This one's nice. It says sine pi over 2 plus pi over 3. This one's nice because it's already been broken up for us as the addition of two angles. Okay. Notice that one of the angles is also pi over 2. Technically, pi over 2, pi, and 2 pi, and 3 pi over 2 are all those key points in a sine or cosine function, or in a tan function as well. So I'm just going to write at the side here. So pi over 2, pi, right? Those are all those x coordinates of the key points when we draw a graph. 3 pi over 2 and 2 pi. These are all considered special angles as well. For these ones though, you shouldn't ever have to use a calculator. So if I say, like, if you have to find sine 3 pi over 2, you should just be thinking of your sine graph and thinking, okay, what is the y value when x is 3 pi over 2? Okay, so these are additional special angles, okay? So you may use those as well. So here, I'm thinking to myself that this looks like sine A plus B, right? Where A is pi over 2 and B is pi over 3. So I just wrote out, I know we're getting used to it now, so you don't have to flip back. Just remember sine A plus B is sine A cos B plus cos A sine B. So now we're going to plug it in. So after that's just plugging A in where you see A and pi over 3 in where you see B. So sine pi over 2 plus pi over 3 is equal to sine pi over 2 cos pi over 3 plus cos pi over 2 sine pi over 3. And now we're going to evaluate. Okay. So sine pi over 2, okay, I want you to think of sine's graph there. So let's just do a little kind of sketch here. So that's 0. This is going to be pi over 2. That's pi, 3 pi over 2, and 2 pi. So we know, and that's kind of 1, that's negative 1 down here. So if we draw the graph of sine, it's going to go up to here, come down, and back up for 2 pi. Okay? So when I'm asking for sine pi over 2, I'm going to my graph and looking at that point, and I see that the value for sine pi over 2 is 1. Okay, so it has a y value of 1. So that's where that comes from here. Cos pi over 3. Let me just do an underline here. Little arrow. Okay. Cos pi over 3, we're going to use a special triangle. So I'm going back up here to cos pi over 3. That's adjacent over hypotenuse, so that's 1 over 2. Plus cos pi over 2. So now we need to think of the cos graph. Okay, so again, you can do if you can do this in your head, that's awesome. For those that need the visual, that's okay too. I always find it helpful myself. Okay, so pi over 2 for cos. Okay, and then it would be pi, 3 pi over 2, and 2 pi. So for cos, we're going to start here. We're going to come down here, down, back up to the max, right? So our U shape. So for this one, which I'll do in orange, so this guy here. So again, we want to know what cos at pi over 2 is. I can see right here that cos at pi over 2 is 0, right? That's my y value. So I have 0. And then sine pi over 3, that would be opposite over hypotenuse, so root 3 over 2. So because root 3 over 2 is multiplied by 0, that's why I have an arrow going right through and saying that just all equals 0. So then my answer is just going to be 1 times 1/2, and that just equals 1/2. All right, 1/2 plus 0, just 1/2. All right, now let's try part B. It says cos 15 degrees. So everyone might go about this a different way, but you should always get the same answer. So for example, when I looked at this, we're obviously going to change this to radians, but just for the sake of continuing on here. Cos of 15 degrees, I immediately thought of as cos 45 minus 30. If you thought of cos 60 minus 45, that's okay too. It still applies. You're going to go through, obviously, with coming up with different values in the process, but your final answer should be the same. So I'm just going to rewrite this in radian form for our unit. So I'm rewriting cos 15 as cos pi over 12. Okay. And that means it's equal to what I wrote here, cos of pi over 4 minus pi over 6. So this, you should be looking at this and thinking that this looks like cos A minus B. So let's use our formula for cos A minus B. So that means you do cos A, so cos pi over 4 times cos B, cos pi over 6, plus, right, it's always the opposite sign, plus sine pi over 4 times sine pi over 6. All right, so let's use our special triangles. Cos pi over 4 is going to be 1 over root 2. Remember, we always try to rationalize the denominator, so we know 1 over root 2 at the side, or sorry, at the side here, so 1 over root 2. Remember, when you rationalize the denominator, you have to multiply top and bottom by root 2, and then that equals root 2 over 2. Okay. Just as a little reminder. Okay. So I'll just put a little star here so you know to look at the orange work here. Okay. All right, so now we're going to do cos pi over 6. Cos pi over 6, if you follow my cursor, is adjacent over hypotenuse, so root 3 over 2, plus sine pi over 4, that is 1 over root 2, which leads you to the orange part again, which is just root 2 over 2. And sine pi over 6 is opposite over hypotenuse, so that's 1 over 2. All right, remember with multiplying fractions, you multiply the numerators, multiply the denominators. So root 2 times root 3 is going to be root 6 over 2 times 2, which is 4. So root 6 over 4. Plus root 2 times 1 is root 2, 2 times 2 is 4. So we're happy here because we have a common denominator, so we can write this as this combined. So we just combine the numerator, right? So root 6 plus root 2 divided by 4. There's another way that you can write this. I'm not sure, you know, the textbook may write it in different ways, so I just want to make sure that you're able to understand both. They may write it like this, or they may have just factored out a root 2. So for example, up in this step here, they might have factored out the root 2 in the numerator, and then you would have been left with the root 3 plus 1. Okay, so this is equivalent to this, because if I were to distribute root 2 back in, you would get the same thing as up here. Okay. So either answer is fine for me. All right, now notice the tan one. I want you to set up your page, follow this black line here. The tan one is going to take a long time to go through. Not that it's super difficult, but it's just more space. and tedious because it deals with fractions, okay? So just make sure that you've planned enough space for yourself here as you go through. All right, so tan negative 5 pi over 12. So I always convert this to degree measure to help me work with the numbers better. Okay, so I know that this is tan of negative 75. So I thought of writing this as, okay, as tan negative 45 minus 30, right? Those two angles subtracted would give me the negative 75. All right, so that means that's kind of my side work there. So I'm going to rewrite tan of negative 5 pi over 12 is equivalent to tan negative pi over 4, that's the negative 45, minus pi over 6. Okay. So this basically looks like tan A minus B, okay, where A is actually a negative answer here, so negative pi over 4, and B is positive pi over 6. Remember, B is considered a positive angle if you mean that the negative is originally there. Okay, so if we see this as A minus B, then B is just positive pi over 6. All right, so just a reminder here in red, here's our formula for tan A minus B. Okay, so we're going to plug this in now. So that's going to be tan of negative pi over 4 minus tan pi over 6 divided by 1 plus tan negative pi over 4 times tan pi over 6. Okay. All right, so the next part you have to think of here is tan negative pi over 4. So notice it's not the same as the other questions where we had positive angles. When you have the positive special angle, you can just go right to the special triangle. When you have the negative version, the negative indicates to you, okay, that you have, the negative indicates to you that you have gone in the opposite direction, okay? So the negative pi over 4, I'm just going to write here, you have gone in the opposite direction as what we're normally used to, okay? So that means you've actually gone in the clockwise direction. So that means that this angle has actually ended up in quadrant. So if you're going negative 45 degrees, that means you've actually ended up in quadrant 4, okay? So tan of negative pi over 4 has a related acute angle of positive pi over 4. So if I go to pi over 4 up here and I take tan of the related acute angle, that'd be opposite over adjacent, so 1 over 1, so 1. However, because it's tan of negative pi over 4, that means this angle lands in quadrant 4. And based on cast rule, tan of any angle in quadrant 4 is negative. So therefore, I just found out, okay, so just look at the blue here. I just found out that tan of negative pi over 4 is equal to negative 1. Okay, so just look at that blue part for now. Okay, so tan, so actually let me see if I can write that in here to make that easier. Therefore, tan is negative. Okay. I'll actually write it here. So therefore, tan is negative. Okay, so that's where the negative 1 comes from. Okay. All right, so the 1 comes from the special triangle, opposite over adjacent. The negative comes from the cast rule. All right, minus tan positive pi over 6. Positive pi over 6 we're happy to work with over here. Tan of that is opposite over adjacent, so 1 over root 3. And when we rationalize the denominator, that's root 3 over 3. Okay. Now divided by, okay, so just to make it a bit visually easier to see, I've put the numerator in red square brackets, and I've put the denominator in purple square brackets, just because it might look a little busy. So now we're doing 1 plus, and then the value from the top, so 1 plus negative 1 times root 3 over 3. Okay. All right, we cannot simplify the numerator or the denominator without having a common denominator. So up here we need a common denominator of 3. So I multiply the negative 1 by top and bottom by 3. Here as well, when I multiply this in, it's just going to be negative root 3 over 3. So I'm going to need to have a common denominator here. So what do we end up with in the numerator? So just looking at the numerator, we're going to end up with negative 3 minus root 3 all over 3. Okay, so that's the numerator. The denominator is going to be 3 minus root 3 over 3. Okay. All right, so I know on first glance, many of you are probably thinking, oh, I can just cancel out, right, this whole expression, because they look similar, and then I'm just left with the negative. That is wrong, okay? Even though it looks nice like that, that's not true because those two values are different. If you went to your calculator right now and you did negative 3 minus root 3 divided by 3, that would give you a different answer than 3 minus root 3 over 3. Okay, so you have to keep in mind the negative here is not sitting on the outside. Okay, the negative is with the 3 in the numerator, so it's a package deal up here. Okay, so we cannot cancel out. What we can do to further simplify is because we're dividing two fractions, let's change it to multiplication and then flip the bottoms. So let's do our fraction rules. So you maintain the top fraction, negative 3 minus root 3 over 3, change to multiplication, and then flip the bottom. So 3 over 3 minus root 3. So in this case here, because you're multiplying, you have a common factor at the top, common factor at the bottom, because you would multiply across here and multiply across here. So the 3's canceled out. You are then left with, okay, so just look at the blue. You're then left with negative 3 minus root 3 divided by 3 minus root 3. Again, you cannot cancel anything out. These are not the same factors. Okay, if you ever have doubts, type it into your calculator. If they are two different values, then they are not the same. So we are used to getting rid of radicals in the denominator when it looks like this, right? When there's a singular radical, and then you just multiply by root 2. This is different. Okay, so what's different here is that this is a binomial in which one of them is a radical. So you cannot just multiply top and bottom by root 3, because while that would help by multiplying this by root 3, when you multiply this by root 3, then you're still left with a radical in the denominator. Okay, so you haven't made your life any simpler. So what do you do when you have a binomial in which one term is a radical and you need to get rid of that in the denominator for proper form, right? So this is improper form right now. Okay, it's the correct answer, but in bad form. So you need to do something called the conjugate. Okay, so I'm just going to write that up here, the conjugate. So the conjugate of a binomial expression, okay, conjugate, okay, is basically uses the same terms as the original binomial, but you switch to the opposite sign in between. So here you have 3 minus root 3, so the conjugate is 3 plus root 3. Okay, that's what you're going to multiply the top and bottom by, right? Whatever you do to the bottom, you do to the top. So let's see what happens when we do that, and I'll show you why we use the conjugate. You're going to see, but it's only going to make sense if we go through it together. So, all right, for this case here, I want you guys to do FOIL. So for the numerator here, I want you to FOIL every term there. Okay, so when we do that, for the numerator, negative 3 times 3, negative 9. Negative 3 times positive root 3, that's negative 3 root 3. Negative root 3 times 3, that's negative 3 root 3. Negative root 3 times positive root 3, that's going to be negative 3, right? Root 3 times root 3 is just 3, negative times a positive is a negative. Okay. Let's do the same for the bottom. 3 times 3 is 9. 3 times positive root 3, 3 root 3. Negative root 3 times 3 is negative 3 root 3. Negative root 3 times positive root 3 is negative 3. Okay, so let me just write in here what we're doing. So in this step from here to here, We were doing FOIL. Okay. Distributive property. All right, what do you notice happened in the denominator? We had a plus version of 3 root 3 and a minus version of 3 root 3. Gonzo. Okay, those are gone. We are so happy about this because the whole point of this was to get rid of radicals in the denominator. This is why the conjugate, multiplying by the conjugate, always works. Okay, because it anticipates, kind of think of like difference of squares. When we did the factors of difference of squares, one positive, one negative, remember we always ended up with only 2 terms left? And that's the same here. We ended up with only 2 expressions left because the 2 middle terms cancel out. All right, so let's finish here. So if I collect like terms in the numerator, I get negative 9 minus 3, so negative 12, and then negative 3 root 3 minus 3 root 3. That's, if I collect like terms, that's negative 6 root 3. The denominator reduces to 9 minus 3, so that's 6. And we actually can do some common factoring here. So I notice that I can take out, if you want, you can take out a common factor of 6 or negative 6. Honestly, it doesn't matter which one you do. So for example, if I took out a 6 in the top, I'm left with negative 2 minus root 3 divided by 6. And then I can cancel the 6's out because those are common factor in the top and bottom. And then finally we arrive at our beautiful answer that's in proper form. And that is, you're left with negative 2 minus root 3. And that is a beautiful exact answer. Okay. No radicals in the denominator. Okay. I know this may seem daunting, but just do a few practice, maybe even on a separate sheet. Try going and tackling this question again after the lesson and make sure that you're comfortable with it. So just remember, conjugate, multiply by top and bottom, do FOIL, and by doing this you should eliminate the radicals in the denominator. All right, so now let's move on to the next example. It says simplify each expression and evaluate. So we've got sine 5 pi over 6 cos pi over 3 minus cos 5 pi over 6 sine pi over 3. So immediately you should be thinking to yourself, this looks like the expanded sine A minus B formula. Okay, they want us to simplify the expression, so they want us actually to work backwards now. Okay, so we want to figure out what was its original sine A minus B formula if this is what it expanded to. So in this case here, the A is 5 pi over 6 and the B is pi over 3. So if I work backwards then, this is basically like me saying sine 5 pi over 6 minus pi over 3. We can't simplify in here until we have a common denominator, so I multiply the top and bottom by 2. So that gives me sine 5 pi minus 2 pi over 6. That's sine 3 pi over 6, and always put in lowest terms. That is sine pi over 2. Part 2 says so that's simplifying. That would be that step here in red. And step 2 says evaluate once you've simplified. So we have to think, what is sine pi over 2? I want you to go back up to the sine graph up here. Sine pi over 2 is 1. So we just evaluated that awful looking expression. We just evaluated it in another way by working backwards. Okay, and we never once used a calculator. Okay. Let's do this one. Cos 7 pi over 12, cos 5 pi over 12 plus sine 7 pi over 12 sine 5 pi over 12. So right away you should be thinking that that looks like cos A minus B, where A is 7 pi over 12 and B is 5 pi over 12. So let's work backwards. Okay. So if this was what we had, that means originally we were possibly given cos 7 pi over 12 minus 5 pi over 12. That equals cos 2 pi over 12, right? They already have the same denominator. In lowest terms, that is cos pi over 6. Okay, so I have simplified the expression. Now part 2 says to evaluate, so I'm going to go to the special triangle. Cos pi over 6 is adjacent over hypotenuse, so that is root 3 over 2. And again, we did it without a calculator. then part C says sine 2x cos x minus cos 2x sine x. So this looks like sine A minus B, where A is 2x and B is x. So this one's going to be really quick because I'm just going to write in sine A minus B, 2x minus x, and that easily simplifies to sine x. And you're done. All right, let's turn over. All right, so this one says if sine A equals 3 over 5, okay, so notice A, I know it's kind of weird for these angles. We're used to doing angles with capital letters. For the sake of these formulas, they always use A and B in lowercase, so just get kind of used to that in the textbook and the homework questions. So sine A is 3 over 5. Sine B, notice different angle, okay, is 5 over 13. Where A and B are obtuse angles. So we know that the word obtuse means that that angle A is angle A and B then are both between 90 and 180. So in radians, that means between pi over 2 and pi. So we were just told, by saying obtuse angles, we were told that the angles are in quadrant 2. Okay, so the terminal arm of A and B land in quadrant 2. So that means it's somewhere in here. Okay. So I'm going to cancel out here. So none of them occur over here. Okay, but they are between pi over 2, okay, and pi. So we have to find sine A minus B. So I know the formula for sine A minus B is here. And let's fill in what we know so far. So we know sine A, that was given as 3 over 5. We don't know cos B. We don't know cos A either, but we know sine B is 5 over 13. So now we're going to have to do some work to find these two pieces given what they already gave us. All right, so let's start by finding cos A first. So if I need to find cos A, so I'm looking here at sine A, okay? So we know sine A equals 3 over 5, okay? We know A lands in quadrant 2 as well, okay? So here's my angle A in quadrant 2. Remember, sine A always refers to opposite over hypotenuse, okay? So that's always, I can also write here, right? So this is always y over r. So basically this gave us 2 dimensions of the right triangle. So it gave us opposite, so it gave us y, right? So that's the y. And it gave us the radius of 5 here. So if we need to find cos of this angle, that means I need x, right? Because cos A is going to be equal to x over r. Okay? So how do I find x? I can use Pythagorean theorem, right? So I know that x squared plus 3 squared is going to equal 5 squared. Okay? Again, we don't know this. The negative 4 is what we're going to come up with for now. So that's x squared plus 9 equals 25. X squared equals 25 minus 9. X squared equals 16. Then you have to take the square root of both sides. And mathematically, we know that if you take the square root of this number, that's equal to plus or minus 4. So this is where you have to make a decision. This is where you have to say, therefore, x is equal to negative 4 because it lands in quadrant 2. Okay, so because we land over here, that means the x values here are negative. So it's negative 4. So when I want to find cos A, that means cos A is going to be x over r. So that's negative 4 over 5. Okay, so that's where that comes into play here. All right, how do we find cos B? Okay. So cos B is dealing with angle B. So we have to work with this ratio now. Okay, so the 5 over 13 of sine, so opposite over hypotenuse. So I want you to do your drawing again, right? We know it lands in quadrant 2. We don't know what x is, but we know we have the y is 5 and the r is 13. because it's sine. Okay. So again, use your Pythagorean theorem. So we know that x squared is going to equal r squared minus y squared. So x squared equals 13 squared minus 5 squared. Oh, sorry, there's missing squared there. Okay. All right, that is going to give you 144. So you're going to take square root of both sides. So that means you get x equals plus or minus 12. Again, x is going to be negative because it's in quad 2. Okay. So here's negative 12. Okay. So therefore, cos b is going to be equal to, right, it's always x over r. Right, so always x over r is cos of an angle. So that's negative 12 over r, which is 13. Okay. So again, this is x over, my apologies, this one here is y over r. All right, so for cos b, I plug that in as negative 12 over 13, and cos a, I plugged in negative 4 over 5. Okay. So now let's simplify. So I get negative 36 over 65, and then these two negatives make a positive, and then 20 over 65. So we get, we can add the numerators and get negative 16 over 65. And we just solved this without using a calculator and just given these small pieces of information. All right, and lastly, to finish off here, it says use the compound angle formulas to show that all these expressions are equivalent. So we have sine x minus pi. So this looks like sine a minus b, right? Let's put that in there. So I'm going to write it as such, right? That's our sine a minus b formula. So that means it's going to be sine x cos pi minus cos x sine pi. So we know cos at pi is negative 1, right? Because at pi it goes down to its min and then comes back up. So sine x times negative 1 minus cos x, and then sine at pi is actually one of its zeros. So that's times 0. So that gets eliminated. So then this expression simplifies to just negative sine x. Right? These two multiply. Sine x plus pi, that looks like a plus b. So we're going to use that formula. So we're going to get sine x cos pi plus cos x sine pi. So notice we're going to get the same values over here that we did there, but just with a plus sign in between. Because this eliminates to 0, right, we're still just left with these two terms multiplied by each other, and so you get negative sine x. And lastly, cos x plus pi over 2. Again, that looks like cos a plus b. And so the general formula for that is here, and we're going to plug in. So cos x cos pi over 2 minus sine x sine pi over 2. So cos pi over 2, so at pi over 2, that's one of cos's x-intercepts, so the y value is 0. And at sine pi over 2, that's when sine is at its max, and its max value is 1. So in this case, this guy gets eliminated to 0, right? And then you're just left with negative sine x times 1, and there you see, they're all the same. So all of these oddly looking expressions all simplify to negative sine x. And you can just kind of verify that there. So sine x minus pi is equal to sine x plus pi, which is equal to cos x plus pi over 2, which is equal to negative sine x. All right, and there's just a summary of all the formulas we learned. Again, just as long as you understand how to use them, that's great. If you are getting used to them where you don't need to look back at it, that's even better. Just make sure you try your homework questions and review these lesson examples, and let me know if you have any questions. All right, good luck.